In this video we are going to look at a heat conduction problem. We are going to apply Fourier's law and we are going to solve a problem that's going to help us understand how does different materials affect design parameters. So without further ado, let's start. So this is our problem. We have a 5 mm thick bottom of a 200 mm diameter pan. So these are sort of geometrical information about the problem, so we're going to mark them. And this pan can be made of aluminum, which has a thermal conductivity of 240 watt per meter Kelvin, or copper, which has a thermal conductivity of 390 watt per meter Kelvin. When used to boil water, the surface of the bottom of the pan, actually, which the question does not say, is exposed to the water at nominally 110 degrees Celsius. So this means the bottom surface of the pan is nominally at 110 degrees Celsius, and this word is actually quite important because it says that nominally means that we are either nominating it, or we may be measuring it, or we want the bottom surface that is exposed to the water to be at 110 degrees Celsius. So now if heat is transferred from the stove of the pan at a rate of 600 watt, what would be the temperature of the surface in contact with the stove for these two materials? So the question is a bit confusing because it says the stove of the pan, but it does give us the heat transfer rate, which is actually 600 watts. So with this information, can we actually find out what would be the temperature of the surface that is in contact with the stove for this pan, which can be made of either aluminum or copper? So let's draw a sketch and solve this problem. So now we have drawn a rough sketch of a pan, and we're going to figure out what information we can get from the statement of this question and relate it to this sketch. So it says that the bottom is 5 mm thick. So this means this dimension is actually 5 millimeters, or we can actually write in our known data thickness L is actually 5 millimeters, or it's actually 0.005 meters in SI units. We also know diameter of the bottom surface of the pan, so we know what would be the diameter D of this pan, which is given as 200 millimeters. So we can actually write in our known column D equal to 200 millimeters or 0.2 meters. Since it says diameter, so this means the bottom surface of this pan is actually a circular surface, or it's like a disc. So because it's a circle, we know this cross-sectional area of this pan, where I'm drawing a red line now, is actually given by pi d squared over 4. So we are going to calculate that area, and that area turns out to be 0.0314 meters squared. So we have some very useful information. Now we know the thickness and the area, and we have converted them to SI units. We also know the amount of heat that is coming through this bottom surface. So this means this pan is actually on top of a stove, and there is heat transfer from the stove through this material that is made of either aluminum or copper, and that heat is actually transferred to the water and heating the water up, and maybe it's boiling, or maybe it's just plain sensible heating that's only causing the temperature of the water to increase. But whatever the case may be, this heat transfer is actually from the bottom of the pan and towards the vertical direction, where I have just drawn a blue line with a thick arrow. To better understand this problem, we can just simply draw this bottom surfaces of the pan and take a closer look. So now I have drawn the bottom surface and sort of zoomed it a bit to help us understand. So we know this thickness, this is actually L. We know the cross-sectional area, which is given by A, and we also know some more information. The question says the surface of the bottom is exposed to the water, so we know water was actually here somewhere, and that means the question is actually talking about this particular surface that I just marked with a red arrow. And the problem also tells us the temperature of this surface, which is nominally at 110 degrees Celsius. So this means this surface has a temperature of 110 degrees Celsius. So now the question is, what's the temperature of the surface that is contact with the stove? So this means the stove is actually here. This is the stove, and the surface I am marking with a blue line, that's the surface which is in contact with the stove, and the question asks what's the temperature of this surface if you make the pan with either aluminum or copper. So now we know that actually there will be two different answers because we are using two different materials, and all we have to do is use our theoretical knowledge of heat transfer or conduction heat transfer to be more precise to calculate this value of the temperature. But before doing that, we have to make some assumptions because we are going to obviously use Fourier's law of heat conduction, because we know heat is being transferred through a solid material, which I am showing you with a black lines, and because it's a solid material, so heat must be conducted through it. It cannot be heat convection or heat radiation, while there will be some effect of heat radiation, but we are actually neglecting that because we are not really that much concerned about how much heat is being transferred to the environment or another hot object that is close to this pan. So to use Fourier's law, we are going to make some assumptions. So we have made 5 important assumptions to apply Fourier's law. First of all, we know that heat transfer must be one-dimensional. We have to assume that heat is being transferred in a single direction for Fourier's law to be applicable, or at least the version we know so far, that one to be applicable. If it was a 3-dimensional problem, or we considered other directions instead of this single direction that I mentioned before, that I am now showing again with a red arrow, from the stove towards the pan, and so through the pan material and then to the water, we are just considering a single direction and we are neglecting any lateral or longitudinal direction. That would make it a 3-dimensional heat transfer problem. Secondly, we are also considering this problem to be a steady state problem, and we know steady state means that with respect to time there is not going to be any change in any particular properties. For example, if you are measuring temperature and with respect to time you are measuring it, so as time progresses, if your temperature value changes, then it's going to be a transient heat transfer problem, or it's going to be an unsteady heat transfer problem. But in order for a problem to be considered as a steady state problem, we can plot the temperature against time, and we're going to find a line like this. It's going to slowly maybe increase, and after some time the temperature is not going to vary that much. So notice when T was 0, you saw a noticeable change or increase in heat transfer, in temperature, which I am showing with an yellow line, an yellow marker. And when you have reached a steady state, there is now no more change noticed in temperature, because the temperature value, or essentially the temperature curve, has become a straight line. So this means this is when the problem has become a steady state problem. But if you are considering it before this time, it was actually a transient or unsteady problem. So for Fourier's law to be applicable, the problem has to be a steady state problem. We have advanced tools to tackle transient problems, and we are going to see them later in this class. But for solving a particular problem when you have no information about time, it's a much better approach to assume it to be a steady state problem and do a simple analysis. And also Fourier's law is applicable for steady state problems. So the third assumption is the pan material is uniform. So this means whatever material you use to design your pan, it has to be uniform everywhere. So if it's made of aluminum, it has to be the same quality aluminum everywhere throughout that cross section or throughout this material that we are considering. Then we are making another assumption that thermal conductivity of the pan material is constant. So we know thermal conductivity changes with respect to temperature. It can also change with respect to time. It can change with respect to direction. But if it changes for any reason, then you cannot use it in Fourier's law. Then we have to consider a different formulation of Fourier's law, which is much more complex. So for simplified analysis, we can safely assume the thermal conductivity of the pan is essentially constant. And also this is a safe assumption to make because we already made an assumption that the pan material is itself uniform. So it is very likely that the thermal conductivity of the pan material is constant. The fifth assumption we are making is that the heat transfer is actually uniform. So this means whatever heat is coming from the stove throughout the pan material, it is the same at every cross-sectional area of the pan. So it's not like in one particular location of the bottom surface of the pan you have more heat transfer, and at some other location in the bottom surface of the pan you have some less heat transfer, and if you sort of combine them then you get a value of the 600 watt. The case is not like that. It's everywhere. It is uniform. It is everywhere. It has to be 600 watt that is coming up through this pan's bottom surface. So once we have made these assumptions, now we can use Fourier's law to solve this problem. So from Fourier's law we have Q equal to Ka times T1 minus T2 over L. So from this question we already know actually Q is the amount of heat that is coming from the stove and through this pan's bottom surface. That is given by Q, and the value of it, the Q or the heat transfer rate is 600 watts. So we know Q, we know L, we know A, and there we actually know two different values of thermal conductivity from the statement of the problem, but we do not actually know T1 and T2. So we know that we have a temperature of one of the surfaces, but we have to look at the problem and understand that is this particular value the nominal temperature of the surface that is exposed to the water is T1 or T2. So from the direction of heat transfer we can see heat is being transferred from this surface I am marking with a blue line, and heat is going through this material that I am showing with the arrow, and then it's leaving this material and going to the water. So this means heat is actually transferred from a higher temperature to a lower temperature, and since the destination of heat transfer is to the surface that is exposed to the water, this means this particular surface is actually at a higher temperature T1, and this particular surface is actually T2. So this means this 110 degrees Celsius we knew is actually T2. So now we know both T1 and T2. We know T2 and we know the location of T1, that is which surface is actually at T1. It is that surface which is in contact with the stove. So now we can actually find out the value of T1. So we are going to just change this equation a little bit to put T1 on the left hand side and all the known quantities on the right hand side. So we are just going to put the values of every quantity here. So Q is 600 watts, L is 0.005 meters, we have area which is 0.0314 in the denominator. We also know T2, and T2 is actually 110 degrees Celsius. So now we wonder what would be our value of K, because we have two materials, aluminum and copper. This means we will have actually two results, so we should actually calculate two different T1s. So one T1 we should calculate for aluminum, so I'm using the subscript AL to denote that, and this whole red boxed equation is actually going to be for aluminum, and we're going to just use aluminum's thermal conductivity, which is given as 240 watts per meter Kelvin. So this is the equation for the temperature of the bottom surface if the pan were made of aluminum. and we're going to use our calculator to find out that T1 for aluminum would be 110.4 degrees Celsius. It's actually an approximate value because I rounded up. And we're going to do the same calculation for copper also, because we want to see what would be the temperature if you use copper and aluminum. So I have written the equation for T1 again, but this time I'm going to use K equal to 390 instead of 240, because this time I'm calculating T1 for copper and I'm using the subscript Cu for copper. So Cu is actually the chemical formula for copper, and we are going to use a calculator to find this value to be 110.25 degrees Celsius. It's again an approximated value because I'm rounding up. So let's box this equation that is for copper. So these are the two values. Let's put the symbol here. So we have calculated two values, one for aluminum, I'm marking it with the yellow, and one for copper, I'm marking it with the green marker. And these are the two values that the question actually asked for. What is the temperature of the surface in contact with the stove for two materials? Okay, so let's now analyze this result. So we know these are our answers. So when we make the pan with aluminum, we see that the bottom surface of the pan reaches 110.4 degrees Celsius when sufficient time have passed and the problem is now at a steady state problem and the pan is at a steady state. The similar thing, but for copper, this temperature would be 110.25. So when you are using a more conductive material, because copper's thermal conductivity is greater than 240 because it's 390. So when you are using a highly thermal conductive material or a more thermal conductive material, the temperature actually doesn't drop that much because let's draw those two surfaces. So this is the surface that was exposed to, say, water, and this is the surface that is exposed to the stove, and this to water. And the question says this surface is at 110 degrees Celsius, and if you make the pan with copper, then the surface in contact with the stove would be at 110.25 for copper, but it would be at 110.4 degrees Celsius if it was made of aluminum. So when you are using a highly thermal conductive material, heat is actually transferred quite well, that now you can maintain a smaller temperature difference between these two surfaces. The delta T can be smaller and you can still transfer 600 watts of heat. But if the material aluminum is less conductive thermally, that means the temperature difference has to be large. So the temperature difference is larger for this case, because if you subtract 110 from 110.4, you get 0.4. But if you subtract 110 from 110.25, you get 0.25. So this is one of the effect of using a highly thermal conductive material. The more conductive material you use, you can have some flexibility to maintain a smaller temperature difference. Another noticeable thing is you can consider that these two surfaces, they're essentially at the same temperature because they're both kind of close to 110, and you can actually just round and neglect this small change of 0.4 or 0.25 degrees Celsius for practical purposes. But the question is, why is that? And the reason this temperature difference is so small, because imagine when you put a pan on top of a stove, initially the temperature would slowly increase, and after some time it's going to start to sort of saturate and flat out, and then it's not going to change that much. And this is the point when we have reached steady state. So initially the bottom surface, maybe when you turn on the stove, say after 2 minutes, it was at 70 degrees Celsius. But at that time that inner surface, or the surface that was exposed to water, maybe it only heat up to say 63 degrees Celsius, and the difference between the two was say at after 2 minutes was only 7 degrees Celsius. But as more time passed on and time went on and on and on, what happened, there was more heat transfer, and the inner surface, or the surface exposed to water, also heated up quickly, and it sort of tried to maintain the same temperature, approach the same temperature throughout this pan's bottom surface. That is, I'm marking with a yellow marker. So this whole material tried to be at the same temperature because you're putting in more heat, and now it sort of reached a steady state. So because we have reached a steady state, this whole pan is essentially at the same temperature, and often we call this condition, the situation, isothermal. This has nothing to do with this plot, so I'm going to erase it. So isothermal means same temperature, iso means same, and thermal means it's actually related to heat or temperature. So isothermal means the whole bottom surface of the pan and the surface that is exposed to the water can be treated as an isothermal surface. So I hope we get some good insight by solving this problem. We get to see if you use different material, it's going to have an impact, even though it's minimal, but it's important to keep in mind that there is still a difference, and this insight is going to help us in designing good products and also help gain insight about many complex heat transfer problems. So thank you, and if you have any questions, please leave a comment.